This is NCEA Achievement Standard 91172. This is NCEA 2. So a disclaimer, while this is on atomic and nuclear physics, this is a starter course. This is an introduction course. And I'm going to do it all in one or maybe two lessons, just in one fell swoop. It's internally assessed. So don't expect to read this or watch these videos and become the next J. Robert Oppenheimer, although you may understand the film a bit more. What we're really doing is we're looking at what exactly an atom is, and we know that atoms are really, really, really small, but we want to know what they look like, kind of what they look like, what they do, what constitutes them, how they behave, how they decay, etc. You're not going to be able to build your own power station or, have your own Manhattan Project, but it's a good start. So, what did we imagine atoms to look like? Here we have John Dalton's model. John is spelled wrong here, I notice. And he basically thought of an atom as kind of like this, as a pool cue. And it's often called the pool cue model. And it's just this one solid sphere. So obviously that's not correct. The next person that had a sort of educated guess was J.J. Thomson. By this time, we discovered that there were subatomic particles, there were negative electrons, and there were positive protons. We didn't know about neutrons yet. And J.J. Thomson thought that the atom was kind of a plum pudding, and you'll often hear this being described. And he kind of imagined the atom to be this kind of blob with these things kind of either stuck in it or kind of floating around, or he wasn't quite sure, but he knew that there were protons and there were electrons in there. He didn't know how they were configured or how they worked or anything like that. The next breakthrough was Ernest Rutherford from Nelson, Lord Rutherford of Nelson, and he discovered the nucleus. So he discovered that the nucleus was full of these positive protons, and around it, kind of like planets, were the electrons. We're going to get to the experiment that did that. Then came Niels Bohr, Danish. He worked out that it wasn't quite orbits, but they were kind of energy levels. So an electron can jump between energy levels, and there are different types of bonds between electrons. This obviously wasn't good. And Edward Schrödinger came along, the same guy who did the famous thought experiment with Schrödinger's cat. And he said that you can't actually pinpoint much about the electrons. You can only give a probability of where they are. So the thing that's interesting in all of these is they're all wrong. We're not still today 100% sure what an atom looks like. We know that it definitely does not look like that, or like that, or like that, or like that. Our guess is that that's the closest we've got. But notice the thing as well is they're all kind of relate to the electron. And it's understandable because the electron does most of the heavy lifting in chemistry. Chemistry is, I've heard it being defined as the study of the breaking and bonding of chemical bonds between atoms, and those bonds are primarily done through the electron. So what does an atom look like? Well, what does the electron shell look like? They have all sorts of weird shapes, and they become very, very, very strange. The electron cloud has weird shapes. The nucleus itself has weird shapes. For our purposes, we're going to kind of imagine more along the Rutherford model, to be honest, than the other two. Although, just note that this is a model. It's not a literal representation of what an atom looks like. We're going to use it as a useful model that we can explain things with. So the main problem with the electron cloud and the atom being expressed like this is that it's way, way, way out of scale. We have this picture of the nucleus in the middle here, this massive nucleus in the middle with these electrons orbiting fairly closely to it. In fact, it's more like this. So this is a model that I did for today. If you had a football-sized nucleus and you went up the Sky Tower in Auckland, the Sky Tower is here, the average distance to the electrons would be almost 7 kilometers away, and they would still be too small to see. In fact, it's debatable that you could see them at all at any scale. They are a point particle. So the distance and the scale involved is enormous. So here's the Sky Tower here. We're way here in Mission Bay, the North Shore. We're out past, well past the zoo, and down here, wherever this is in Auckland. I don't know. I'm from Wellington. But to scale, I mean that's the Auckland CBD. So it is an atom is mostly empty space. There's nothing in here, and this is one of Rutherford's great discoveries. The first experiment that we're going to look at is Crookes tube. So this is commonly known as the Maltese cross tube. The reason it's called that is because this shape was a Maltese cross. It was pretty a definite shape. So how does this work? We have a cathode, which is essentially just a piece of metal, and one of Crookes' great discoveries was that it worked in pretty much any metal. And if you ran an electric current through it so that it almost completed a circuit, there was a gap there that will kind of induce electrons to move off it. So this is a piece of metal. We're not going to go into the naming or the mechanics of how it works, but it makes the metal negatively charged and has a positively charged anode here. And these electrons kind of jumped off. And Crookes discovered that it wasn't haphazard, that they move in a straight line. He thought, well, that's very interesting. So he put that into a vacuum tube. Vacuum tubes were all the rage back then, and they were just starting to become miniaturized. So they put it in a vacuum tube, and lo and behold, it still worked. So whatever was causing these electrons to move, he didn't call them electrons at the time, it must be something inherent with the metal and inherent with the electricity. So what happened is that if they fired these electrons, some of them would hit this cross and would be stopped. The obstacle is earthed, and then there would be a fluorescent tube at the end, and there would be a shadow of this cross here on the fluorescent screen. So what did that prove? It proved that the rays travel in straight lines. It proves that the rays seem to have energy and momentum. So what he also did was he had a little paddle. So this is a Mika paddle. And same setup, but now these electrons hitting this very, very light pedal. In fact, I've got one that I can probably dig out, although I live in Wellington, so there's not much sunlight. It will actually turn this wheel. It's obviously not enough to generate much electricity, but it will convert this electrons into kinetic energy. It will move something. It will do work. He found that it was affected by the voltage that was put between these plates. So voltage is a charge difference between these two plates. This one's negative, this one's positive. So if we increase the voltage, lo and behold, we get more electrons coming out. So these electrons are so small that we can't really see them or measure them, but we can measure their effects. They can exist in a vacuum. They're dependent on electricity, and they go in straight lines. He also noted that it didn't really matter which metal he used here as his cathode. They all emitted energy. Some were better than others, but they all emitted energy. Next thing he did was he introduced magnets. So he has a magnetic field now, and he found that it deflected. It essentially bent these electrons. Now remember, this is a vacuum, so he realized that these electrons, they must have something to do with electricity. They move in straight lines, and they can be bent by magnets, further proving the link between magnetism and electricity. The next major experiment is J.J. Thomson the Senior's experiment of the cathode ray and the electron gun. And this experiment is kind of similar to Crookes' experiment. The difference being, let's get rid of that. The difference being now, instead of magnets, where he also used magnets, he used charged plates. So the top one is positively charged, the bottom one is negatively charged. The variables that he could control, he could control the electron gun, how often it spat out these electrons. He could control the voltage, which is the charge difference between those two plates. And he could also change the magnetic force field, and he could change the distance between these two plates. So when we accelerate an electron through this field, of course, there's no field there immediately. But when we introduce a charge differential, that is a voltage, we start to see something really, really interesting. And we start to see that the beam is kind of bent. It's obviously not to scale. This is nowhere near scale. And we're also going to ignore relativistic effects here. We're going to sort of treat these electrons as if they're little marbles being pulled towards this plate. And he reasoned that they must be these electrons, which he called corpuscles, after blood vessels, blood cells. They must be negatively charged because they were bent towards the positive plate. So it's a common misconception that he worked out the charge. He actually worked out the charge to mass ratio. And he worked out by changing this plate voltage, the amount of bendiness of these electrons, one of a better word, increased as the voltage difference increased. And he also noticed that it didn't matter which, a bit like Crookes' experiment, the metal that the electron came from, it gave the same effect. He got the same numbers, which means that electrons are universal. They are just a quality of metals. They are emitted from metals. When we put a nearly closed electric circuit through it, they will emit electrons at a predictable rate. So he didn't work out the exact charge, but he did work out the charge to mass ratio, so C over M, and he deduced one of two things. He either said that each of these electrons has a comparatively massive charge on it, which isn't really true, or that the electron is infinitesimally small. The charge compared to the mass is huge. Individually, these electrons do not have much of a charge, but cumulatively, when you've got trillions and trillions and trillions and trillions of them, quadrillions of them, they add up. Again, this is a schematic. This is not to scale. Definitely not to scale. If you want maths I've kind of left that there. I'll put this up on the website. The maths is not really as important as the sort of insight that J.J. Thomson reached. So he deduced that electrons are subatomic particles. They are emitted, they have a universal quality, and they are affected by an electromagnetic force field between these plates, and they are negatively charged, and they have a massive charge to mass ratio. The next major experiment is the Millikan experiment. This is an American experiment in 1909. So the setup for this is a vacuum again. Again, this is obviously not to scale. And we have a positively charged plate here at the top, a negatively charged plate at the bottom. And this is as close to a vacuum as they had at the time. And what they did was they introduced a droplet, and this is obviously, like I said before, not to scale, but this is a tiny, tiny, tiny piece of oil. And when they release that, they will look at it through a microscope, and they would see, as you would expect, the oil drop just falling under the effects of gravity. Not much to see. Okay, then he kind of thought, well, let's introduce a voltage. So let's put a voltage across this. Let's spray a droplet, and it fell slower. And they did this thousands and thousands and thousands of times. We've got very precise measurements. So look at what they can control. They can control the distance. They can control when the oil droplets move out, and they can carefully control the voltage. So when we introduce more voltage, we will reach a point where this droplet will in fact stop. And when we have that situation very, very carefully measured, there will actually be a time where it will go backwards. We can sort of balance this droplet. So let's look at the maths behind that. At the top here, we have a negatively charged plate, and at the bottom we have a positively charged plate, and they're connected through let's just say a battery, something like that. And we have the oil drop here. Okay, what are the forces acting upon this oil drop? Well, the only forces are the force from gravity, and that's going to be Fg is mg. We know what the mass is. We know what gravity is. Gravity is going to be 9.81 and a bit meters per second squared. So we can work out the force moving downwards. The force that's moving, that's pulling this thing upwards, what's that? Is when it's floating, is going to be the force from the electric field. And that's going to be, from memory, that's going to be EV, where E is the electric field strength, V is the voltage. And we can simplify this even more so that E is ED, isn't it? Yes. No. This is going to be QE. And where Q is the charge on the droplet. And we don't know what that is. But we can work it out because E is V over D. So Q times the voltage divided by the distance, and the distance is known, it's known in meters. If we set these equal and opposite to each other, we know everything except this Q variable, and therefore we can work out what Q is. And Millikan noted, and again, this is why they did it thousands and thousands and thousands of times, very, very, very carefully, that the Q always jumped in discrete amounts. And he reasoned correctly as it would, this is proportional to the number of electrons. So you can only have a discrete whole number of electrons. You can't have half electrons. Maybe you, if we want to debate that, but we can work that out. The amount of change in the charge from one electron to two electrons is the same. So from this, we worked out the charge on the electron. So let's say that we had one electron. When we found different charges, and we found it was 4.8 times 10 to the minus 19 coulomb. And then when we did it again, we found that it was 3.2 times 10 to the minus 19 coulomb. And when we did it again, it was 1.6 times 10 to the negative 19 coulomb. Well, there's a jump there of 1.6 times minus 10 to the minus 19. And in fact, this was the lowest charge you could get. So he correctly kind of guesstimated that the charge on an electron was about 1.6 times 10 to the minus 19 coulomb. So a tiny, tiny, tiny amount of charge per electron, but a lot of electrons. A lot times not much is something. The last experiment that we're going to look at is Rutherford's classic gold foil experiment. This was first done in 1909 with Ernest Rutherford and Ernest Marsden and Hans Geiger, the person who gives his name to the Geiger counter, in the same year as the Millikan experiment in the University of Manchester. So what this is the setup. We have a alpha source. So alpha source is essentially a helium nucleus that's been charged. It has a high amount of energy, and we fire this at a very, very, very thin gold foil. You may think of the gold foil like tin foil. It's even thinner than that. You probably would have been able to see through it. What Rutherford expected to see was something akin to the plum pudding model, where if we have our atom here, it's kind of this blob with the protons and the electrons in it. This one here, a little bit more. It's a little bit more involved. The proton seems to be the whole thing. And we fire the alpha particles, they'll just pass right through them without interacting. What Rutherford found, in fact, was that when he fired them, some of them were deflected. In fact, some of them actually bounced back. So if we look at the experiment, we're going to start firing these beams off. So here come the helium nuclei. We're firing them off fairly low energy, and again, this is not to scale, and this is certainly not in the ratio that you would expect. So he expected them to pass right through, and he found that, yep, in fact, most of them did pass right through as if nothing had happened, as just as you'd expect. But he noticed that a 1 in 8,000 roughly were deflected or bounced back, which makes no sense whatsoever. And when he noticed this, he noticed that 7,999 of them went through, but these ones that came back, we have to account for that. And he also noticed that they didn't sort of fly off randomly. There was some method to the madness. They were flying off at these angles, and a certain proportion would bounce back. a way smaller proportion than is shown here. So it's as much a mathematical feat as a scientific feat that Rutherford achieved. And he worked out that the helium atoms here are mostly empty space. The gold atoms are mostly empty space, as we showed before with the Auckland Sky Tower example. So the nucleus, the most of the mass must be highly concentrated in a very, very, very small part of the atom, and that's the only thing which will interact with these other nuclei. So he knew as well that it must be highly positively charged. So he said the only way that we can account for that is if we have a nucleus in the middle and it's surrounded by a cloud or shells or orbits of these electrons. The electrons are negatively charged, the protons positively charged. Rutherford didn't know what to call this, so he kind of thought, well, it's a bit like the nucleus of a cell that you'd see under a microscope, so he called it the nucleus. He noticed a discrepancy later on with the mathematics in that the nucleus was about half as massive as it should be, and Rutherford accounted for that by theorizing and proving the existence of the neutron, which is another nuclide in the nucleus which has no charge and is roughly the same mass as a proton. So again, what it proved that the nucleus, most of the mass, 99.999% of the mass of the atom is in the nucleus. The nucleus is tiny. The electrons are tiny and even more tiny and far away. So that's the last of the experiments that we're going to be doing. The next video is going to be on radiation and radioactive decay.
What just happened?
I don't know.